So today I'm going to talk about after the carrier we talked electron, we also talked hole, and now today we are going to talk about a new carrier which is not a one particle like electron and hole, but is a joint union of two particles. We call it exciton. We call it exciton, and exciton is nothing but electron hole pair combined coulombically. This is a charged species, so this is coulombically a bound system like hydrogen atom. The origin of this particle is, for example, every material has a valence band which is naturally filled once some energy is incident on such a system, say in the form of light or any kind of energy, thermal, heating, and so on. Then, for example, this is energy incident on the system. Electrons attain higher energy and they jump to the next band. We call that conduction band. We call it a conduction band. So they jump from valence band to conduction band. Depending on the energy, they can be here, here, here in this band. And once this electron jumps from valence band to conduction band, it leaves a vacancy here, which we call absence of electron. That is having a tendency to attract electron because electron is missing here. So we assign it a charge positive opposite to the electron, and now this electron is reaching here, and this electron is always attracted back to this vacancy where from it has been created. So in virtually this forms a state, we call this a bound state. This is bound to this is not free. So this pair, let me take another color to say this pair, electron and hole, electron in valence band and hole in conduction band, is coulombically bound. We call it exciton. So many properties of crystals are defined on this candidate, exciton. Like we do have many kind of properties based on electron and hole. So this will be the another third particle we will be going to talk about today. Uh, so this is, I start here from electron hole pair. So we have electron hole pair, a particle, bound particle like a hydrogen atom, bound coulombically. I hope this definition is clear, all the words. And this is often formed by an absorption of energy in the form of a photon, which promotes an electron from valence band to the conduction band, from valence band to the conduction band, leaving behind this guy hole. Same thing. In nature, we have here two kinds of excitons. This exciton-based physics is a very interesting physics. This needs a little more attention. So we have two kinds of excitons. We'll be having one we call Mott-Wannier exciton, and another we call Frankel exciton. They are remarkably different kind of excitons and show a different kind of properties. So basic definition is, okay, basic difference between these two kind of excitons is on in relation to the binding energy. One is more bound and one is little bound. More bound means the Coulombic force between the electron and hole is very, very strong. C, I put here. In one case, which is perhaps Mount Rainier, no, Mount Rainier is weak. So, in a Mount Rainier exciton, the Coulombic force is between the electron and hole is very, very less than the Coulombic force between the Frankel exciton. So Frankel exciton is strongly bound. And when two particles, say one electron and one hole, when the force of attraction is this, since attractive in nature is one is positive and one is negative, when the force is very, very strong, naturally they will be living close to each other. So they will be living close to each other. While as when the force is weak, like in case of Vernier, then maybe electron is as free that it has no relation with the hole. It can move very, very away from the hole. And hole is similarly so free from the electron that it can go anywhere. It has its independent identity. It lost the joint identity. So in one type of exciton, we have a weakly bound uh, electron and hole pair system, and in another kind of exciton we have strongly bound system. So in one case we can say that electron and hole behaves independently, and in another case they behave just a one bound system like hydrogen atom. So when they are free and when they are bound, what is going to change? How is it going to make a difference? For example, this is mentioned here, the Mount Rainier, which is weakly bound, it contains the binding energy is just 10 MeV, 10 million milli electron volt. While as the Frankel exciton kind of thing is bound by 100 milli electron volt. So this is strongly bound. If you want to break this kind of exciton, you need to impart some 100 MeV energy. While as if you want to break this kind of bound system, you just need 10 MeV. And just to make a comprehensive understanding here, that the room temperature, which is room temperature, room temperature, which is we take as 25 degree Celsius here. And if you convert this 25 degrees Celsius, it is around 300 kT, 300 Kelvin. And if you convert 300 Kelvin into energy, okay, using this Boltzmann law, then you see that the room temperature in the energy form is, because it's a thermal energy, it is 25 m milli electron volt. Okay, this is here important to point out. The room temperature or thermal energy naturally at room temperature is 25 MeV. So this kind of the Mount Rainier type of exciton, which is having a binding energy of just 10, cannot be stable at room temperature, because as it is formed by some kind of absorption, immediately it is broken back or disintegrated, because it is produced in a 25 background energy. 25 MeV energy is always available in the system, and it is bound only by 10 MeV amount. You need to impart 10 MeV and it's broken. So this cannot be found at room temperature, this kind of exciton. So how can then you say that there are some excitons like Mount Rainier formed in this kind of material? Then you need to, reduce the room temperature. You need to go to something helium like temperatures. You need to reach to some Kelvin, 5, 10, 100 Kelvin, and so that to observe this kind of exciton or spectroscopy based on this exciton. So this exciton is not found in room temperature because room temperature is more than this, so it will not be stable. While at this kind of exciton, which has a binding energy of 100 MeV, once this is formed, this is quite stable at room temperature because 100 MeV is not available in the room. We have only 25. So 25 cannot break this system. This is quite stable. So we can find easily Frankel type exciton at room temperature, and we cannot find Mount Vanier type exciton at room temperature. So these are two kinds of excitons. So one which is just free, not bound, that is we call also weak or Mount Vanier. We can say that this is delocalized. They are not localized, they are not bound, they are free. And the other is a localized one. They have to move together. So why one kind of materials show one type of exciton and another material show another type of exciton? This depends on the dielectric constant of the material, which is varying from material to material. So in the materials which have dielectric constant less or equivalent to 2 is going to show us one kind of exciton, while as there are materials where it is around 10, so that's going to show us another kind of exciton because this what we call the electric constant is playing role to in role to see that which kind of exciton is facing more coulombic force or less coulombic force, because through the coulombic expression we know F is equal to 1 by 4 pi epsilon naught. So epsilon is going to play a role. So higher the epsilon, less is the force. Less the epsilon, higher is the force. So this is going to play a role in defining a weakly or strongly bound exciton system. So in one kind, what I mean localized and delocalized. For example, this is our crystal. Now let me show it a little bigger. Let's say these are the crystal planes. Then one kind of exciton, which is electron hole pair orbiting each other, can make a big, because every particle is in orbital motion naturally. So one somewhere they are making a big path, big elliptical path around which they keep on moving. So they are very far each other. This is a weak exciton, or we call it Mott Vanier exciton. And in another kind of crystal is they are very close, so we can show them there like this. So it contains two particles, one particle and two particles. Here similarly it contains one particle maybe here, one particle maybe here. We will show the real picture, good picture soon, but this is just to have an idea. Okay, once they are in a motion, orbital motion, they, like electron or hole, which we have done yesterday, will be having a Bohr radius. They will be at with respect to some center at some path. Okay, once they choose this elliptical path, so with respect to this center, they will be having some radius. We call that for electron. This is the electron Bohr radius, and for hole, this is the Bohr radius, which we calculated yesterday. It depends on this permittivity of free space and medium. Same is here. It also depends on the mass. If mass is just S mass, or if mass is shielded or having some effective mass due to interactive kind of nature situations. And now today we are not with either with electron or with hole. Today we are with an exciton, which is a system made of two particles, electron and hole. So the total mass of this will neither be electron nor hole, but a new kind of mass. We call it reduced mass. So you might have done two body system. If you have one body M1, if you have another body M2, you can find the reduced mass of this system, which is M1 M2 by M1 plus M2. So same expression I wrote here. So today we have two particles jointly connected through Colombian force and define a just single particle with reduced mass as mu given here. So we need to calculate not the Bohr radius of electron like yesterday, nor we need to calculate the Bohr radius of hole, but today we need to calculate the Bohr radius of exciton, which I mentioned here. That is not linked to the mass of electron nor mass of hole, but a reduced mass of the single particle called an exciton, which is mu. And if you put back these expressions and break them into this kind of factor AE and AH, you see they will be equivalent to this. Or in terms of the rest mass, you calculate, use these all expressions. I have used these expressions. This is solved here. Just think I did not write from here and from there. You can understand that. I'll share these notes with you today, inshallah, also yesterday and today's note. So this is in terms of the rest mass, like we did for the electron and hole. In terms of rest mass, the Bohr radius for the exciton is this. So today, as per the definition, you want to see a material behaving as an anode due to the exciton. You need to reach to this scale. So this Bohr radius is, proportional to this dielectric constant of the material. So higher the dielectric constant, higher will be the Bohr radius. This is constant, and A0 is a hydrogen Bohr radius, which is constant, and this kind mu will be changing. These two parameters will be changing from material to material. So more dominant effect is due to this dielectric constant. So it's a this Bohr radius is a dependent on the dielectric constant, which is a function of frequency. This varies with the frequency under which you are observing things. So, but often it is being taken for simpler reasons on optical frequency to avoid that confusion that you can move to any frequency, but it's just taken often the results are taken at optical frequency. So we fix it to optical range. And if you fix it for optical range, which is mentioned here, E optical, dielectric constant epsilon at optical range is for this kind of material. I have taken just example, cadmium, selenium. Okay, let's calculate the Bohr radius for this. The effective mass of electron is here 13% of the rest mass of the electron. So it is reduced. Similarly, the hole, which is little larger than this, effective mass of hole is 45% of the rest mass of electron, and at E optical frequency around 9, it is 9.7. And calculating, you can use these two to find the mu. Mu is a reduced mass, which is here Me. I hope you know these two body interaction, Me and M whole. क्लासिकल मैकेनिक्स में आप लोगों ने पढ़ा होगा वसीम के पास perhaps. So this is Me plus Mh. So you can find the mu, and once you find the mu, then using this expression, E epsilon is known, M naught is known, Bohr radius of hydrogen atom is known, mu you can calculate, and it turns out that 5.07 nanometer or 50 angstrom, 50.7 angstrom crystal can show us a nano-like properties due to the this particular exciton. So if you want to have a cadmium selenium nanomaterial and observe a exciton property, you need to ground a material of this range. Similarly, okay, you remember this is, I have to calculate it, compare it again. So this is 5 nanometer. Now let's move to another kind of crystal where this optical epsilon is not 9.7 but just very small, 3. So for example, we take one crystal, zinc oxide. In zinc oxide type of crystal, this is very small. A mass of hole is same as the mass of hole in the cadmium selenium crystal here, which was here 0.45, but the effective mass of electron was here 13, but here in the zinc it is 0.24. And so this varies here from one crystal to another crystal, and this varies. So these two parameters vary. And once you put back the and calculate the mu, and you calculate the Bohr radius, turns out to be this much, 1.24, or you can say 12.4 angstrom. 1.24 here for zinc oxide, but 5 in the another crystal CDSE, which is very, very large. So large Bohr radius and smaller Bohr radius. Large Bohr radius means the electron and hole is at very, very larger distances each other. So they might be weakly bound and they can take some sort of independent nature, and we can call them weakly bound or delocalize it, or we can call them Mott Wannier type of exciton. So for the materials where epsilon is large, we have Mott Wannier type of exciton, which are very far away each other. While as for the crystals where the dielectric, uh, this epsilon dielectric constant is very small, we have, you know Bohr rate is very small, means the species are very close to each other, and we call them, they will be strongly bound due to Colombian force. They are very close to each other, and we call them Frankel type of exciton. So in this way, we have two types of excitons. For one, you need to impart more energy to break them or to separate them. For the other, that can be perhaps at room temperature. So this all is represented here in this diagram also. One which is having a larger Bohr radius or larger elliptical orbit is Wannier exciton. This occurs in inorganic type of semiconductors, and this is okay. Let's say hole is at the center, the electron is orbiting around it. While as in case of the Frankel type, which is strongly bound, they are in very close proximity and they are strongly bound, not easy to delocalize them. In this way, we have two types of excitons. And now, if you look for properties like optical properties, absorbing photon, emitting photon, and other kind of properties linked to this kind of exciton, they will vary from here to here. So today's lecture was uh, to realize that excitons are of two types: weak and strongly bound, and we call them Vanier and Frankel, and the spectroscopy and their size, and we could have feeling of how much a dimension of nanomaterial has to be in order to observe properties linked to this kind of exciton. And here I will end this lecture today and stop. Okay, anyone wants to say anything? आप लोग बात करो कोई. आप लोग बात करो, ठीक है? हेलो। इंटर ओके, okay, let us stop here and see you next week, inshallah. I'll share these type of notes, and I recorded this video also. I'll share this video also. Okay, assalamu alaikum.
Okay, sir. Allah Hafiz.